Hello. Okay, so in this lecture, I'll be talking about the derivative of an exponential function and logarithmic function. Okay, so this is section 3.2. So here I decided to skip these two sections. All right, 2.6 and 2.7. If you see the schedule from the blackboard, well, you can see these two sections on the schedule. But I skipped. I decided to skip these two sections. All right, so I will start now from section 3.2. So in this section, well, before we start about the derivative of exponential and logarithmic function, first let's just revise few things that we did in chapter 2.4. All right, so in chapter 2.4, we talked about the definition of a function. The definition of a derivative of a function. All right, so if we say we have a function y is equals to f of x, then the derivative of those kind of function, well, we can take the derivative function like this using this idea in chapter 2.4. All right, so and the next one here I'm showing here is this thing. If you take the limit where h goes to 0 of the function e to the power h minus 1 over h. So these kind of function, when you take the derivative, when you take the limit of these kind of functions is always 1. Oops. It looks like L. Let me just write 1. Oops. I don't know why I'm not getting used to it, these things. Okay, 1. There you go. So, okay, so this is, you can take this this thing as a fact or formula or whatever you want to say. Okay, so let's take this as a fact. All right, we will be using this fact later on. So now let's say now we have a function f of x is equals to e to the power x. All right, so these kind of function, we say this is an exponential function. All right, and this e right here on the bottom, e is a special number where e is equals to 2.71 blah blah blah, something like that. It's a special number. So these kind of functions, when we take the derivative of these kind of functions, well, we can use this formula right here, because we know that the derivative of any function, we can use formula to get the derivative. All right, well, probably you notice that, well, let's say if we have a function f of x is equals to, let's say, x to the power 3. Okay, so in these kind of function, we can still get the derivative of this kind of function using this definition, right? But we talked about the power rule, right, on chapter, I think, 2.5. So we can take the derivative of this kind of functions using the power rule, where we can say, the reason we can take the power, well, we can use the power rule here is, here on the base, we have a variable, and on the power, there is a number. All right, but with these kind of function, which we say it's an exponential function, has a number on the base and the variable on the power, right? So this kind of function we say exponential function, and this kind of function we just say a regular function. Yeah. So now to take the derivative of this kind of function, we can just simply bring this 3 down here, and now we get x to the power, a new power, which is going to be 3 minus 1, which is 2, right? This kind of function, we can take the derivative just like this. But now here, it's different. Okay, so here, let's use this one right here. So first, to use this one to take the limit, let's find the value of f of x plus h. We know the f of x is e to the power x, but f of x plus h is e to the power. Now, instead of x, now we're going to get this whole thing x plus h in the power. All right. And also this is equals to, we can say e to the power x times e to the power h, right? Because when we have two terms with the same base, then we can combine this to a single base and just add the power or just combine the power, right? That's exactly, well, basically this is in the opposite direction, but these two are still equal, right? Okay, now after that, now we got the value of f of x plus h. Now let's get the value of this whole thing, f of x plus h minus f of x. So f of x plus h minus f of x is, well, f of x plus h is this, e to the power x minus e to the power h, minus f of x is e to the power x, right? And then, oops, what did I do here? This is, sorry, this should be times, yeah, e to the power x times e to the power h, which is f of x plus h, minus f of x is e to the power x. All right, so we got this whole thing. Now let's, well, on the denominator, we just have h. So now let's take the limit of that. So let's take the limit of this whole thing, which will give the f inverse of x. So let's take, now let's use this whole thing. So now the derivative of f of x is equals to limit of h goes to 0, right? And f of x plus h minus f of x is right here. So let's just write that here again. Or before we do that, let's do one more thing here. Well, we have e to the power x times e to the power h minus e to the power x, right? So on these two, I can factor out e to the power x, right? So if I factor out e to the power x, the remaining terms are e to the power h minus 1, right? Okay, so f of x plus h minus f of x is e to the power x times e to the power h minus 1, right? And over, okay, we got the numerator part, and over, we still have this h. All right, so now it looks like we can use now, well, since I said this is a fact, right? It looks like I can use this fact somehow here. All right, so here what we can do is, well, but the thing is we still have this e to the power x extra here, right? Because here we don't have any e to the power x, here we have e to the power x. But the thing here is, since we are taking the limit of h goes to 0, or the limit of h, so in that case, this will be like a constant. So we can basically just take this out. So I can say e to the power x, just bring that out and just take the limit of h goes to 0 of e to the power h minus, sorry, e to the power h minus 1 over h. All right, so here we have multiplication here. So e to the power x times this whole thing. Now the thing is, the limit of this thing is, well, we know that this is equals to 1. We said that this is a fact. Well, even though we didn't prove it, let's just take this as a fact and let's just use that here. So this means we'll get e to the power x times this whole thing is just 1, right? So it looks like, okay, we still get e to the power x. So it looks like when we take the derivative of e to the power x, the derivative of, well, this thing is still e to the power x. All right. Okay, so here, since we said that this is a special kind of an exponential function where e is a special number, where e is these kind of number, right? But we still have another kind of exponential function as well, right? So that kind of function, well, we can still take well, let's say, f of x is equals to b to the power x. All right, so here b is not equals to e, because we said it's a special kind of number here, right? We say e is this kind of number. Now here b b could be anything, but it cannot be 1, and it has to be greater than 0, right? So if it is satisfied, this b satisfied, or the base satisfied this condition, then we can also say this is an exponential function. Now, when you take the derivative of these kind of function, well, I'm not going to show the proof of this, but well, you can just memorize this thing here. So when you take the derivative of these kind of exponential function, well, the first thing, well, it will still be here. First, we still write the same thing. Now, the only extra thing we're going to have here is we're going to have natural log of whatever the base is b. All right. This is similar to the derivative of e to the power x. Okay, so when you take the derivative of this thing first, it will be the same thing times natural log of the base b. All right. So let's do an example. Let's see this thing with an example. So let's do the first one, which is, let's take if this y is equals to 4 times e to the power x plus 5 times x to the power 4. Okay, so when we take the derivative of this one, well, derivative of y, we can also write y prime. Now, since this 4 is multiplied with e to the power x, so in these kind of case, when we talked about this, I think on chapter or section 2.5, so in these kind of case, this will stay the same, and just take the derivative of e to the power x, and we said that the derivative of e to the power x is still e to the power x, right? Because we said the derivative of this is still e to the power x. That's what we got here, right? So using that fact here, we can say e to the power x plus, so now when you take the derivative of this, well, this is just the regular function. We can just use the power rule. So first one, this 5 is still going to stay the same. And bring this 4 down here, times 4, x to the power 4 minus 1, which will give 4 times e to the power x, so 20 times x to the power 3, right? Similarly, let's say we want to take the, let's do another problem. We're going to take the derivative of y is equals to 2 to the power x, 2 to the power x plus 3 to the power, 3 times e to the power x. All right, so on this one, now I want to take the derivative of this one. Okay, now this is also an exponential function, right? Which is for this one, which is similar to this. All right, so when you take the derivative of this kind of exponential function, then the derivative of this one, the first thing will stay the same, 2 to the power x times, now only the extra thing here we have is log or natural log of 2. All right, so that's the derivative of 2 to the power x. Now the derivative of 3 is attached with this e to the power x, so 3 will stay there, and when you take the derivative of e to the power x, we still have e to the power x, right? Because derivative of e to the power x is still e to the power x. All right, there you go. That's the answer. Okay. Now let's talk about the derivative of logarithmic function, or let's just say log function. Okay, so log function, Well, the first one, y is equals to natural log of x, right? So when we take the derivative of a natural log of x, but this natural log of x is also a log, right? This natural log of x is same as log base e. And e we said is a special number, right? E is equals to 2.71, something like that. Now, when we take the derivative of these kind of thing, it will be 1 over x. If you have natural log of x, and when we take the derivative of this, it's 1 over whatever the thing is here, 1 over that thing, x. All right, so this is also formula. I'm not going to derive this, but I'm just giving you the formula, all right? And another one, another log function is log base b. All right, so natural log is log base e, with e being a special number. And another one is log base b, where again b could be anything that is greater than 0 and b not equals to 1. All right, so when you take the derivative of this kind of function, the first thing, just like I did here, I'm going to take the derivative of this kind of log function. The first one will be 1 over x. Okay. Now on these kind of log function, if the base is not e, then there will be one extra terms, which will be 1 over natural log of whatever the base is, b. All right. And you can also take this as a formula. All right. So using these things, now let's do an exam. Well, let's do a few examples here. So the first one, let's say we have y is equals to log base 4 of x. So here, well, now the base is 4, which will be these conditions, right? So then on this thing, we can say y inverse is, well, first thing would be, it will be 1 over x times, because we have x here, that's what we have, 1 over x. And another term, it will be 1 over natural log of the base is 4, so natural log of 4. So 1 over natural log of 4. All right, so this is the derivative of this function. All right. Let's do another one. Let's say, instead of saying y, let's say this time f of x is equals to natural log of 2, or no, natural log of x to the power 2. Natural log of x to the power 2 plus 7e to the power x plus 3 to the power x. Okay, so here on this problem, okay, this x square is attached with this log function, right? Or this natural log. Okay, so here what we can do first, before taking the derivative of this, what we can do is we can use one of the property that we did back in chapter 1. So if we have log of any base m to the power k, then in this case, this power, we can bring this power down here. So this will be k times log base b of m, right? And also, well, this ln is also a natural, well, this natural log is also a kind of log, right? This is also log. So we can still use the same property here. So here we can bring this 2 down here. Okay, so this will be 2 times natural log of x plus 7 times e to the power x and plus 3 to the power x. So once you do this, now we can take the derivative of this. Well, you have to take the derivative of this uh, at the same time. All right, so you cannot do like take the derivative of this and just write the same thing here. So when you take the derivative, you have to take the derivative of all of these at the same time. Or you have to take the derivative of all of these at the same time. So here now, well, since now this 2 is attached with this now natural log of x, so the 2 will stay there. And when you take the derivative of natural log of x, it will be 1 over x, right? Times 1 over x plus 7 is attached with this e to the power x, so 7 will stay there. And when you take the derivative of e to the power x, it will still be e to the power x. And now when we take the derivative of these kind of exponential function, where now base is 3, then the first, it will stay the same thing with extra term, which is natural log of 3, right? Okay, that's the derivative of this function. Okay, let me do one last problem. Let's say, okay, this equation is going to be a big equation. F of x is equals to, now let's say 7x squared minus natural log of x to the power 8 plus 4 times e to the power x minus 5 to the power x plus now there is one new terms, log base 9 of x to the power 5. Okay, so now here, when we take the derivative, or before we take the derivative here, we can do a few things first. So here, well, we cannot move this to just like that. Well, we can move this to here. That will be a derivative of this kind of function. So we're not taking the derivative yet. So let's just write the same thing here. But now here with this log function, with this, yeah, this is also log. So with these kind of log function, we can bring this thing that is in the power down here, right? Using this property here. So then this will be 8 times natural log of x plus 4 e to the power x minus 5 to the power x plus, again, we have a log function. Now log base 9 of x to the power 5. So again, we can bring this 5 down here. So this will be 5 times log base 9 of x. All right, now after this, now we can take the derivative of this. So the derivative of x will be f prime of x. So now when we take the derivative of this, well, since we have a variable on the base, so I can use the power rule for this one. So I can just bring this 2 down here. So this will be 7 times 2 times x to the power. Now we're going to have a new power, which will be 2 minus 1, right? Minus, okay, 8 times take the derivative of log of x, which will be 1 over x, right? For this one, 4 times derivative of e to the power x is e to the power x minus the derivative of 5 to the power x. Now, the variable is in the top, so this is an exponential function. So to take the derivative of this, okay, the first one will be the same thing, 5 to the power x times natural log of 5, right? Plus, now on this one, still have, well, there is this 5 attached with this whole thing. So we just have to take the derivative of this log base 9 of x. 5 will still stay there. 5 times, now take the derivative of this whole thing, log base 9 of x. So first one, it will be 1 over x, right? I'm using this formula right here. Okay, so 1 over x times 1 over natural log of whatever the base is, 9, right? Okay, so yeah, this is it for this section, for this 3.2. All right. I think you guys will have, well, the exam will come up really fast. You know, since this is a summer course, so I will, for the exam 2, I will ask from, I'll start from, for exam 2, I'll start from 3.2. So I'll ask from 3.2 and whatever I'll cover before exam 2 will be this exam. All right. So, all right. See you later. Thank you.